We'll start today's lesson with a question about lines. And so it says, how can we tell if two lines are parallel or perpendicular? So let's just do a nice easy example. I'm going to do this from their slopes. So like y equal to, and let's do 2x plus 3 versus y equal to, and let's do 2x minus 2. And then let's do y equals negative 1/2 x plus 3. So two of these lines are parallel and two are perpendicular to each other. And so let's take a look. So how do we know if two lines are parallel? From their slope. And the idea is that the slope is the same. So up above here, if you look, these two lines have the same slope, so they're parallel to each other. Whereas this line has a slope of negative 1/2, so it's not parallel to that line or that line. And you think about it, you can see this from the picture. If you draw x-axis and a y-axis, it's pretty obvious that if you have two lines that are parallel, they will have the same slope. Right, so here's a line. Here's a line, and if they're parallel, their slopes are exactly the same. Whereas if you have two lines and they're perpendicular, then the idea is that, well, one of the slopes is a negative reciprocal of the other. So you can say, you know, one of these slopes is the negative reciprocal of the other. For example, this has slope 2, whereas this has slope negative 1/2. And so if your slope is 2, so if m is equal to 2, the negative reciprocal, so the slope that is perpendicular, is equal to negative 1/2. So these two lines are perpendicular to each other, and this line is actually perpendicular to this one too. So these two are also perpendicular. So it's easy to tell if two lines are perpendicular to each other. You just look at their slopes. So let's look at one more quick example. Like if you had y equal to 5x plus 2. If you want to create a line that's perpendicular to it, you could just make negative the reciprocal of slope, so negative 1/5 x plus, you can put anything you want here, plus let's do 4. So these two lines should be perpendicular when you look at them. And if you graph them, what you'll basically see is that you have this line here, which looks something like, oh, I don't know, that. And then you'll have this line here, which will look something like this. And then the perpendicular means they'll cross at right angles. So let's do this in a color. Let's do this in blue. So they'll cross at right angles. So that's how we tell if two lines are perpendicular or parallel from their slope. Today, we want to talk about quadratic functions and their models. We're down here on the modeling section. So one thing I want to talk about, so we talked about this form. This is called the vertex form. And today we're going to talk about the standard form, which you may be a little bit more familiar with, which is y equals ax squared plus bx plus c. And we often use this form if we want to find the roots. So if you have a parabola here and you want to find its roots, which means find the x values that you would plug in and get back 0, then we'd use this quadratic formula to find x. It's one way to do it. So as an example, let's do 2x squared plus 3x, and let's do minus 7 equal to 0. And so I would identify my A. My A is 2, my B is 3, and my C is equal to -7. And I would pull out this quadratic formula, which I will give you on the exam, and I would say x is equal to a negative b plus or minus the square root of b squared minus 4ac all over 2a. And I would just plug in. So I have a negative 3 plus or minus the square root of 3 squared, so that's a 9, minus 4 times 2, so 4 times 2, and then times a -7, so 4ac. And then this is all divided by 2, and there should be an a there, 2a, so 2 times 2. And you can use your calculator then to compute these two numbers. And so on your calculator, you take, let's do left parenthesis, -3, and first we'll add the square root, so second square root, 9 minus, I have 4 times 2 times a -7, in parenthesis, divided by 2 times 2, so divided by 4. So one x value, x is approximately 1.27. Or we could have, instead of adding, you can hit second enter. So say instead of taking 3 plus, you could have 3 minus that, and you would get back -2 point, and we'll round it 2 decimal places, so 7. So those are my two possible answers. So let's look at a word problem involving this quadratic formula. So here we have the number of TV channels that the average U.S. home receives has been soaring in recent years. The function c of x equal to 0.16x squared plus 0.46x plus 21.36 can be used to estimate the number of channels C an average U.S. home received x years after 1985. Predict the year that the average U.S. household received 100 channels. Okay, so the idea is you have this 100 channels, and you have to ask yourself, is that x stuff or is it c stuff? And x stuff is years, so you're not going to plug it in for x, you're going to plug it in for c. And so what we have on this, we're trying to figure out the years, so we'll have 100 equal to, and then we write the formula on the right, 0.1 x squared plus 0.46x plus 21.36. And what we can do is we want to use a quadratic formula, so we need to move over this 100, so we'll subtract 100 from both sides. And we'll wind up getting, let's write it all on the left-hand side here, so I'll have 0.16 x squared plus 0.46x, and then it'll be minus, and I have to figure out 21.36 minus 100. So if you have your calculator, you can take this 21.36 minus 100, and then hit enter, and you're going to get out negative 7.78, so minus 78.64. So that's 64, and that's equal to 0. And so if you look at this, you can identify your A, that'll be your A, that'll be your B, and this will be your C. And so we have x is equal to, and to copy down the formula, it's always good, so negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And we simply plug in here. So I have negative 0.46 plus or minus the square root of b squared, so 0.46 squared, and then minus 4ac, so minus 4 times 0.16. And then this is all times c, which is negative 78.64. And then that's all divided by 2 times a, so 2 times 0.16. And you want to put this into your calculator to crunch this number. So let's take a look and see what we have. And so I get this left parenthesis negative 0.46. And I'll do plus first, so plus the second square root of 0.46 squared, so raised to the 2, minus 4 times the 0.16, and then times negative 78.64, in parentheses for the square root, in parentheses for the top, and then divided by left parenthesis 2 times 0.16. And if I put this in right, it should get out about 21 years. So this is approximately, let's round to the 2 decimal places, so approximately 20.78 years. Now that's if I add, if I do the plus. Let's see what happens if I do the minus. And so if I do the minus, we come back up here and I subtract. I get a negative answer, which doesn't make any sense because it goes back in time, so I want to exclude that answer, so I don't care about that answer. All I care about is this answer right here. And they want to know the year in which it happened. So this is 20.78 years after 1985. So to give my final answer, I should add 1985 to this. So if you take 20.78 and you add those number of years to 1985, you get out in 2005, let's say. So in 2005, this should occur. So here's my answer right there, in 2005. All right, so the next problem we want to look at is quadratic regression. So remember, regression is the process we follow to find the best fitting whatever. So if we're going to do quadratic regression, it may be that we have a bunch of points here, and they're not perfectly quadratic, but there exists this sort of best fitting quadratic function that approximates these points here. And so let's take a look at the problem. So here's example 5. And so in this example, the table lists the number of Walmart employees, E, in millions and T years after 1987. So here are the years. So this must be 1987. 5 years later, I guess would be, what, 1992. 10 years later, 1997. And down here you have millions of employees. So you can see in 2007, 20 years after 1987, you have 2.2 million employees. So the first thing we want to do is simply plot the data on our calculator. So let's do this. So remember, to plot things, you're going to hit the Stat button, and then you're going to hit Enter under Edit. And you're going to go over here, to fill these in. You can clear these things out if you want. I guess you hit Delete. Right? So delete, 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 and I'll delete them out if you want. Or you can just overwrite them. So I have 0, enter, 5, enter, 10, enter, 15, enter, and 20, enter. And then I go over to the right-hand column, L2 here, my list 2, and I'm going to put the outputs over here. So 0.20, enter, 0.38, enter, and 0.68, enter, 1.4, enter, and then 2.2, enter. Check the data you put in there because it's easy to make a mistake, so I think it looks good. So I'm going to hit Y equals. I'm going to turn on my plot. So now my plot is on. And then I'm going to hit the zoom button and go to not zoom fit, but zoom stat, because I'll zoom in the stuff underneath the stat button. So hit enter on this, and I should get a nice looking plot that looks sort of like a parabola that's sort of opened up. And I want to plot this. So right over here, I'll do part A, because there are various things I want to graph. And so on this plot, I have a vertical and a horizontal axis. So I have this. The horizontal is T. The vertical is E. They stand for different things. So this is the T years. So time T. And you can put, let's say, years after 1987. And then for the outputs over here, we have, well, these are employees. Set employees E, and this is in millions. So the units here, the number of employees is important. And then you can just kind of approximate the dots if you want. You can put, 0 here if you want. You can put 5 here, 10. There's not that many, so you can draw the little hash marks, 15, 20. And then I would probably just approximate the points. So it looks like it starts a little bit down here, goes up a little higher yet, then a pretty big significant jump, and then a pretty big significant jump. And so that's sort of what it looks like over there. And then in part B, I want to use quadratic regression to find a quadratic model for E as a function of t and round the regression parameters to 4 decimal places. So to do that, you simply hit the Stat button, go over to Calculate, and then go down to quadratic regression. Last time we did linear regression. Now we'll do quadratic regression. Hit enter, and out pops my answer. So for part B, let's just write it, I guess let's do it right here, part B. We'll move this over. So for part B, what I have is, this is my output y right here, and so I'm going to write, instead of y, I'm going to write E. So I have E equal to, into 4 decimal places, so my A is 0.0047. And this says x squared. Now my input is t, so I'll use t, so I have t squared. And then plus 0.0055. And of course it says times x, but my input is t. And then finally we have plus this constant c, which is 0.2051. And so there's my function E. If you want to see if it's a good fit, you can graph it on your plot just for fun. We can do this. So let's do it just so you can see that it's a pretty good fit. So 0.0047 x raised to the 2 plus 0.0055x, and then plus 0.2051, and then hit the graph button, and you should see that this graph, this quadratic function, gives you a great approximation for what's going on here. It fits it almost perfectly. All right, so now what we want to do is, over here in part C and D, we want to use this equation we found, this regression equation that we found, the model, and answer some questions. So in part C, it says what? It says use this quadratic model to estimate the number of employees in the year 2012. So 2012, is it employee stuff or time stuff? And obviously it's time stuff. So this implies that my t is equal to, it starts in 1987, so you just count up. If you start in 1987, 3 years gives me to 90, and then 10 years to 2000, so that's 13, and then plus 12 is 25. So my t is 25, and all I need to do is plug 25 in for t. So E of 25 is equal to, and so I'll take 0.0047, and I'll multiply it by 25 squared, and then I'll add 0.0055 times 25, and then to that I'll add the 0.2051. And so let's do this on my calculator. And on my calculator, I can actually use, since I graphed this thing, I can actually use this graph. And so it's a good exercise in using a piece of technology to solve a problem. So what I'm going to do is I'm going to hit trace, and there are going to be a few problems that occur. So if I hit trace and I try to hit 25, it's going to clear the screen. So what exactly happened here? So go back to graph, and when you hit trace, you'll notice that it says P1 up here, which means you're on the plot. So you're not on the actual graph. But if you hit down, now it says up here, this is actually the formula we found, the equation we found. So now I'm on the graph. And so now it'll let me put in 25. But if I do this and hit enter, oh, it says error invalid. So hit down and go to, and it's going to go to the issue. It says I cannot understand 25. And that's because your window is too small. So over here, your window goes from -2 to 22. You want to up this window and maybe go to 30, let's say. And might as well start it at 0, it doesn't matter. But you want to go to 30 so it includes 25. So I'll refit this window. So go to zoom, zoom fit. And now I get a nice looking graph. And when I hit trace and go down, because I want to be on the actual graph, and now I hit 25 and hit enter, it's going to spit out a number. So this is approximately, and this is a 3.2, actually it's equal to, just write the whole number, 3.2801, and this is million employees. And so that's my answer here. In part D, this was an input question, meaning you plug in for the input. Part D should be then an output question. So use a quadratic model to estimate the year in which Walmart employs 5 million people. All right, so for this one, part D, 5 million, that's not T stuff, that's E stuff. So you're going to plug in just 5, because E's in millions, and set it equal to this formula, 0.0047 T squared plus 0.0055 T, then plus 0.2051. Now you can solve this a number of ways. You can move over the 5 and use a quadratic formula, or you can graph the left and graph the right and intersect. We're going to graph the left and right, and do the intersect, so you can kind of see how this works again. And so on here, I have my y equals. I have the formula. I'm going to hit enter, because on the other side I have a 5, so on y2, I'll hit 5. And then I'll just hit graph and see what happens. If you see a line go across the page, you're great, but you don't. So that means your window is probably too small. So I'm going to go from 0 to, let's do 50 years. And then I'll refit my window. So zoom fit. And so what happens is this graph goes up, and there's that 5 million that comes across. And I want to intersect these two curves. So I'll do an intersect. And when you do intersect, so second trace pulls up the calculate menu and go down to intersect. So I'll hit enter on intersect. First curve good, second curve good, give it a guess, just hit enter and it'll jump right to that intersection point. And so it looks like T is about, it says 31.36 years, so T is approximately 31.36 years. And we want to know in what year, so in which year, right? Estimate the year. And so I'll add, this started in what, if you go back up to the top, it started in 1987. So 1987, and we'll add then, so second, quit, clear, we'll simply add 1987 to that 31.36. So if you just hit plus, it actually pulls down the answer you had before. So that's kind of neat. And so you actually get 2018. So in 2018. All right, so it's kind of a neat little thing. If you 31.36 plus 1987, yeah, is equal to about 2018. But if you just hit plus after you find the intersection, it'll stores that answer in there. So 2018, Walmart should reach 5 million employees. Now this is just a model, so remember that it won't fit forever. Walmart may plateau, and it may go, the number of employees may actually go down, and it may go up. It may be some sort of cyclic function later on. So it just models it over the time period. So it's good for the next couple years or so. So 2018, I guess that's not too far away, and so you may be able to use this model to predict what's going to happen.